Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. First of all, in the 5th Borobudur International Symposium 2023, allow me to thanks for this opportunity to present our research with the title Local Stability Analysis of Dengue Transmission. The second time, let me introduce our team. I am Arista Fitri Diana, and the authors' team are Latifatul Aulia and Zakaria Bani Ikhtiar. We are from Department of Actuarial Science, Faculty of Science and Technology, ITESA Muhammadiyah Semarang. First, this is the overview for my presentation. There are introduction that contains dengue fever, fatality case, and modeling. And then the second, this is the methodology that contains the diagram of proposed model, dynamic model, basic reproduction number, stability analysis, and then the numerical simulation, and the last, the conclusion. First, the introduction. The dengue fever is the disease caused by the dengue virus and transmitted by Aedes aegypti mosquito. This mosquito is the cause of dengue fever and transmits the virus when it bites and sucks the blood, usually attacks in the morning and evening. That the fatality case for dengue fever can cause quite serious complication and potentially even causing death, so that we can modeling the dengue transmission for identifying a pattern that can be exploited. There are many previous works in modeling dengue transmission that are already published. In this research, discuss the default SAIR model by adding the death variable for spread of dengue virus. This is the diagram of proposed model. There are two parts in this model. The first for the human and the second for the mosquitoes. First, the infected mosquitoes bites the susceptible human, so that the susceptible human become the exposed human, and then the exposed human become the infected human. The infected human has two possibilities. They become recovered human or become dead human. And then the second part is the model for the mosquitoes. This is the susceptible mosquitoes that bite the infected human, so that the susceptible mosquitoes become the exposed mosquitoes, and then the exposed mosquitoes become the infected mosquitoes. This is the description of the variables. SH is susceptible human, EH is exposed human, IH is infected human, RH is recovered human, DH is dead human, and the variables for mosquitoes are SM for susceptible mosquito, EM for exposed mosquito, AM for infected mosquitoes. And then this is the description of the parameters. UH is the natural death rate of human. Beta H is the mosquito's human transmission probability. Rho H is the human incubation rate. Gamma H is the rate of human infected become decades. And then mu M is the natural death rate of mosquitoes. Beta M is the human mosquito transmission probability. Rho M is the mosquito's incubation rate. And then 1 minus gamma H is the rate of human infected become recovery. From the diagram of proposed model, we can create the dynamic model. This is its differential function that can describe the relation between the variables. There are the DSH, DEH, DIH, DRH, DDH, and for the mosquitoes, there are the SIM, DEM, and DIM. For the dynamic models, we get the equilibrium points. There are two equilibrium points. The first is disease-free equilibrium, or we can say DFE. This is the N 000 m per mu m 0. And then the second equilibrium point is the endemic equilibrium, or EE. There are SH star, EH star, AH star, RH star, SM star, EM star, IM star. This is the endemic equilibrium point. And then we create the basic reproduction number by using the matrix of the spreading virus. This is Fix and Vx. We can create the basic reproduction number. Now we have the basic reproduction numbers like this. And then after we get the basic reproduction number, we can use the basic reproduction number to analyze the stability analysis of equilibrium point. The first equilibrium point is the disease-free equilibrium. The first theorem that the disease-free equilibrium will be locally asymptotically stable if the basic reproduction number less than 1 and unstable if the basic reproduction number more than 1. And then the second term for the endemic equilibrium, that the endemic equilibrium state is stable if the basic reproduction number more than 1 and unstable if the basic reproduction number less than 1. And then we can simulate the dynamic models by using Maple software version Maple 15 and the journal reference. And then we simulated the dynamic model with the initial condition are SH 0, EH 0, AH 0, RH 0, DH 0, and for the mosquitoes there are SM0, EM0, and the last IM0. And then the parameters value we can see in the table: mu h, mu m, beta h, beta m, rho h, rho m, gamma h, and b. This is the numerical simulation. We get the graph of model simulation. This is susceptible human, recovered human, exposed mosquito, exposed human, treat human, infected mosquito, infected human, and susceptible mosquitoes. For the graph, we get the basic reproduction number is 5.173. So the basic reproduction number is more than 1. So the endemic equilibrium state is locally asymptotically stable. And then from the analysis and the numerical simulation, we can conclude that theoretically it's proved that the dynamic transmission depend on basic reproduction number, which have a crucial role for the stability system, where we got that the model simulation with this is the basic reproduction number is 5.173. This shows that the death variable increase so that the endemic condition is happened. Okay, this is the results for our research, and thank you for your attention.